Okay, so we heard an overview of the aims of the Prospect instrument package from Mahesh earlier today, and thank you for making my job slightly easier. But this talk focuses on our efforts towards honing our ability to use the Prospect instrument package to meet the objectives of working out what resources of interest are available at the lunar poles and to help facilitate human exploration of the moon and further. So just to recap for those that might not know, two of the defined science goals of Prospect are first, the quantification of volatiles trapped at the lunar polar regions, and second, to characterize these volatiles in regards to their sources. That's identifying if the volatiles found at the poles are from solar wind implantation, asteroidal or cometary impact delivery. And our team in Manchester has kind of kicked off the cross-lab calibration process, focusing in on the noble gases. So those are helium, neon, argon, krypton, and xenon. And the aim is really to calibrate the instrument capabilities against some lab-based standards. So why do we use the noble gases? Well, noble gas systems form one way of quite robustly characterizing volatile inventories. And that really comes down to the fact that noble gases are incredibly chemically inert, meaning there's little in terms of chemistry that can complicate the measurements. They're also found fairly evenly spread across the solar system, and for the most part are in low enough concentration that small deviations within their isotopic ratios can easily be detected. Further to all of that is the amount of complementary science that you can also carry out using these systems. However, as this figure shows, they're not without their own drawbacks. The illustration it shows how complicated some of these processes that can modify the noble gas inventories of samples can be. So, as I mentioned, the work is the start of efforts to calibrate the measurements made by Prospect on the lunar surface. And to do this, we selected two lunar soil samples from the Apollo 14 and Apollo 16 sample collection. These were selected based on what we thought to be representative of the most likely dry case scenarios that we may find upon landing. Aliquots of these samples were distributed for measurement at 3 institutions across the Prospect science team. And the idea being that we would cross-collaborate, I keep saying collaborate rather than calibrate, cross-calibrate across these labs and then to the lander itself. So our setup in Manchester is a Thermo Fisher Helix multi-collector mass spectrometer. Our standard measurement protocol is to use 2 aliquots of any given sample, one for light noble gases, so helium, neon, and argon, and one for heavy noble gases, that are krypton and xenon. We sequentially heat a sample using a 917 nanometer laser, and the extracted gases, we extract gases at defined laser power steps. And these gases are then purified across a range of getters and cryogenically separated into single element phases. We release these and measure them in sequence using the mass spectrometer, kind of in a similar way to what we expect the Prospect instrument will be able to do. We've also recently modified these protocols to test whether subsplitting the extracted gases into known volumes would cause any unforeseen issues within the data reduction process or the measurement itself, as this is something that should be possible using Prospect. And the aim here is to collect all the noble gas data we can from a single aliquot, which is important given, particularly with Prospect, we're limited to the number of samples that we can extract. So these are the release profile data from the 2 calibration samples that we have measured. As you can see, we extract about 75 to 90% of the total inventory of each sample within 0.1 watt of heating power. This early release is likely to be surface implanted solar wind, which we do confirm using isotope ratio data, but I've opted to not show that here. On top of that, we achieve within our laser heating, we achieve sample melting at about 3 watts. I mean, that changes slightly because of how lasers couple with different minerals. But then we get a second release at 3 watts of mineral lattice bound gases, which include your cosmogenic gases. And this is how our measurements compare to literature data. As you can see, the submature sample 14163, which is the yellow diamond, appears to contain greater concentrations of gases than the more mature sample, which is the purple square. We wouldn't normally expect that. We would normally expect solar wind implantation to correlate with maturity. And we suspect that this indicates that maybe the measured sample aliquot used in one of the analyses is either oversampling or undersampling the agglutinate content of the parent soil. Not expecting that slide. Just going to jump to this one. So we can look at just the major isotopes of each noble gas element and assess the gas inventory for its fit to known volatile reservoirs. So here we're comparing it to solar wind, which is the black line with the white diamonds. We take each major isotope and we ratio it to 36 argon to give us a nice baseline comparison. And as you can see, there is similarity between the samples and solar wind, but there's notably a depletion in the light isotopes and an enrichment in the heavy isotopes relative to the expected solar wind composition. And this really hints back at that illustration earlier that shows how complex noble gas processes can actually be. We do suspect that this is solar wind. It's just been, there's been a small amount of gas loss or sample disruption that has led to this fractionation. So what can we achieve? Just touching upon the kind of science questions that we can answer with noble gas measurements. We can take the measured values and fraction them into the amount of gas that's attributable to each contributing source. Here we're using solar wind and cosmic ray produced gases to enact a simple lever rule 2-component mix. So this plot shows how each heating step is progressively depleted in solar wind type gases, which is expected because they're surface absorbed, surface implanted. And due to, from this fractionated gas, we can also calculate parameters such as the cosmic ray exposure age, which indicates how long a sample's been exposed to the cosmic ray flux, which is typically synonymous with residence within 1 to 2 meters of the lunar surface. So we calculate that this sample appears to have been exposed for 28 million years, which is that and looking at the parentless argon-40, which is degassed argon-40 derived from radioactive decay of potassium-40, which has then been reimplanted into the surface of the sample by UV light ionization. serves as a semi-quantitative measure of when the sample was last exposed to the solar wind flux on the lunar surface for more than a few thousand years. And we actually can't calculate that value for this sample because it seems to have been so recent that our errors overlap with a negative age, which would indicate it's been freshly exposed on the surface. So just to kind of wrap up, in terms of prospect and these calibrations, we may be able to examine the regolith from different depths. We may be able to examine when regolith from different depths was likely last exposed on the surface, how long the sample was exposed for, the contributions of different source reservoirs within the sample's total inventory, all through noble gas systems. And such characterization may allow us to understand the duration over which the volatiles have been trapped, the duration over which the volatiles that are trapped at the poles may have accumulated, and may also possibly indicate how long it would take for those concentrations to replenish, which is a factor that is fairly important in providing sustained access to the lunar surface in the future. So thank you.